In this installment, we are going to look a little bit more closely at the behavior of FG perpendicular and FG parallel as we change the angle theta of the incline. We derived in the last installment that FG perpendicular is mg cosine theta. Well, let's talk a little bit about the cosine function. The cosine function, this is our 0 and our amplitude, and let's say this is 2 pi radians, pi over 2, and 3 pi over 2. What we know with the cosine theta is it behaves like this. It doesn't erase. There we go. It behaves like this. Now, an inclined plane can go from 0 degrees to 90 degrees. So we are concerned primarily in the first quadrant where cosine of theta goes from 1 to 0. So just by that token, recognizing that the force of gravity perpendicular is being scaled to the cosine function, scaled by the weight to the cosine function. Oh, it starts at 1. Oh, so we know that FG perpendicular equals FG. And when we get to the last at 90 degrees, so at 0 degrees, we know that the force of gravity perpendicular equals the force of gravity, 1. And we know it's 0 at 90 degrees. That component of gravity perpendicular is 0. Now let us see why by constructing the forces here. So if we have an object sitting on an inclined plane of 0, we have our force normal and our force gravity. It is not accelerating vertically, so we know the two are equal and opposite. So indeed, the force normal equals the force of gravity. And the force of gravity is the force of gravity perpendicular. If we jump to our middle setting and we draw a line parallel to the inclined plane through the end of the weight, like so, and we then draw a dashed vector and a dashed vector, this is our force of gravity perpendicular and this is our force of gravity parallel. So what we can see is going from 0 to this intermediate angle, the force of gravity perpendicular is now less than the weight. Because we have a right triangle, the weight is the hypotenuse, so the force of gravity perpendicular must be less. We'll use the same process on this lesser angle. Again, what we will do is draw a line parallel to the inclined plane through the end of the weight vector. Then we will draw a line that's an altitude to that parallel line. This is FG parallel, or FG perpendicular, and this is FG parallel. So as we go from 0 degrees, we see that the force of gravity perpendicular is decreasing, and it's decreasing because the force of gravity must always remain the hypotenuse, and the force of gravity perpendicular is a leg. When we drop this down lower, we can see that the force of gravity perpendicular will rotate and become the same size as the weight. Similarly, when we raise it, force of gravity stays pointing in the same direction. Force of gravity perpendicular gets smaller. We employ the same technique here. We draw a line parallel through the end of the weight vector. We now draw a vector that is perpendicular to the incline, and we can see now that's the force of gravity perpendicular, how small it's gotten indeed. But notice now we have a much bigger force of gravity parallel. And by the time we get to 90 degrees, if we try to draw another line parallel, it is the wall. And so what we've observed occur is perpendicular going from the size of the weight, decreasing, decreasing, decreasing until it's 0. And we began by saying that when it's 0, Fg is equal to the force of gravity perpendicular. Let me reverse that. Force of gravity perpendicular equals the weight. And by the time we get to the wall, the force of gravity perpendicular equals 0. And that is exactly how cosine behaves. And again, the only thing I would suggest you know is how to derive this relationship, ft perpendicular being mg cosine theta, and conceptually to be able to model making that shift in your mind. So now let us move on to the force of gravity parallel. We will begin by drawing, we'll start in the middle this time, and we will draw a line parallel to the inclined plane that runs through the end of the weight. Then we will construct a line that is perpendicular to the incline and to that parallel line. That is our FG perpendicular, and this is the FG parallel. We'll move to the left to a smaller angle. Let's not use that line. Let's make a better line. We'll again draw an altitude to that line, perpendicular to the other line. And this gives us force of gravity perpendicular, and this is the force of gravity parallel. So we can see as we are decreasing the angle, the force of gravity parallel is decreasing. When we go in the other direction to increase, we draw our inclined plane parallel to the inclined plane, the line parallel, and then we draw the altitude. We get this force of gravity perpendicular and this force of gravity parallel. And we can see that is larger yet. Now, when we get all the way to 90 degrees, the line parallel is the wall. And when we draw an FG perpendicular that's an altitude, the FG perpendicular equals 0. And parallel is that part of gravity that runs parallel to the plane. And we can see then that FG parallel is the force of gravity. FG parallel is gravity. That force, that part of gravity pulling it down the incline is all of gravity. All of gravity is pulling it down the plane, and none of it's pulling it into the plane. When we go to the other end, the far end where the angle is 0, we can draw a line parallel, like so, and then draw a perpendicular line. And we can see then that there is no part of, we draw our force of gravity perpendicular, which would exactly follow the weight. There is no component that is parallel. So we see that the force of gravity parallel is 0. Mapping the sine function from 0 to 2 pi. And our altitudes, we know that sine of 0 is 0. And the sine function behaves like this. We are, of course, again, concerned about the first 90 degrees, and sine starts at 0 and increases to a maximum at 90. And that's exactly what we saw. We see that scaling the weight by sine gives you the force of gravity perpendicular, or force of gravity parallel. So parallel parallels the behavior of sine. So whereas perpendicular equals gravity at 0, parallel equals gravity at 90. When we have a vertical wall, none of gravity is pulling it into the wall. All of it is pulling it down the wall. When we are at 0, all of gravity is pulling it into the surface and none of it's pulling it sideways. And so these are how the components behave and why as we go from 0 to 90 degrees. Now it is in the next installment that we're going to do that real life application and examples.